Great. So last time we talked about how to prove Van Kampen's theorem and its applications to cell complexes. And I mentioned at the end of class last time that what we would do next is go back to how we computed the fundamental group of the integers. So we used a cover of the circle by the real line. And then we took path on the circle and we lifted it up to a path on the real line. And we proved that the only ambiguity was where do you lift the base point. Once you choose where to lift the base point, then there was no ambiguity in lifting a path or in lifting a homotopy. And so we were able to read off the fundamental group from the preimages of the base point, which gave us the integers. So we want to study this sort of situation more generally. And this topic is called covering spaces. So we want to generalize this situation. So what we want is a map. And we're going to say that a map evenly covers X if there is an open cover of X and every U in this open cover has P inverse of U equal to a disjoint union of, say, phi alpha with phi alpha open subsets of X tilde, and the restriction of P, this covering map, to each of these open sets is a homeomorphism. Right. So if this happens, we say that the open set U is evenly covered, and that this covering map evenly covers X if you have a cover by such evenly covered open subsets. If we want to refer to these subsets of the inverse image, we call the V alpha a slice of P above U. Okay. So, of course, our first example is the cover of the real line over the circle. You can also cover so we're going to look at the circle over itself. So what you want to do is think of the circle as sitting inside the complex plane. So these are the vectors, complex numbers of modulus 1. And then you want to map the circle to itself by just raising a complex number to the nth power. All right. So in terms of how we were thinking about the circle in R2, this, of course, is just going around the circle n times, either clockwise if n is negative, or counterclockwise if n is positive. All right. So to visualize this, let's say that n is equal to 2. Then if here is the circle you're over, then viewing it from above, you might have something that looks like this. All right, so this circle sits above it twice, and you have a projection down to this other one. Or if you're looking at it from the side, then it might look something like this. All right. So again, you have two copies of the circle, and they sit above this one. Right? It doesn't self-intersect, so it's a little awkward to draw, but that's the idea. Another example is, let's say you have the two circles, and you identify a point in each circle with the other. So we have a bouquet of two circles. So here is, for example, a cover where we're going to have, say, this is loop A, this is loop B. So this base point is going to have 3 points lying above it. And if you think about what would happen if you lift a path, each of these is going to have one A that is leaving it, and one A that is returning to it, and similarly one B that is leaving it, and one B that is returning to it. So let's see, we could draw something like this. Let's say you have one B like that, and then over here a B like that. So here I have a path, a B path leaving this point, so I also have to have a B path returning to this point. So let's say you have something that looks like this. I was also sitting above B. So now every one of these base points, these copies of the base point, has a path labeled B that is either coming to it or leaving it, one of each. And similarly, on the other side, I should have A, so let's say that I have also one path A going like that. But this time, let's join this all the way up here, and then have one path from here that winds its way like that, but that is going down. Okay, so we ended up with this graph up here, and of course in this graph these lines are not identified. I've just labeled them with the loop that they identify with downstairs, right? And the projection is the obvious map down. Okay, so that's an example of a covering space for this bouquet of two circles. And it's easy to see that because this is a graph, a cover is going to have to be a graph as well, just because it's you have a local homeomorphism there. Okay, so those are some examples. If you look at the textbook, page 58 has a bunch of examples. So I encourage you to do that. Okay, so as I just said, a covering map is a local homeomorphism. Which is a good moment to stop and remind you what we mean when we say that some property happens locally, or perhaps tell you what we mean when we say that something happens locally. So to say that a map is a local homeomorphism, what we mean is that for every choice of points, and for every choice of points, there are neighborhoods, in this case, for which P is a homeomorphism, but moreover, this is true for arbitrarily small neighborhoods. So one way of saying that is that if given any point x tilde in X and a neighborhood of this point U, then there is a smaller neighborhood such that P restricted to V is a homeomorphism. Right? So again, it's for arbitrarily small neighborhoods, you get a homeomorphism. So every covering map has this property because you just look at these slices. But this is not enough to know that you have a covering map. So for example, if you just take the covering of the circle by the real line that we had before, then just restrict this. Its restriction, say to -1, 1, is a local homeomorphism, but not a covering. And you can see that the base point, so 1, if you view this as sitting inside the complex plane, that is not evenly covered. Okay, so as we were just recalling a moment ago, when we used a covering space to compute the fundamental group of the circle, the important property that this map had was that we could lift any path and homotopy of paths. So we want to be thinking about this for general covering spaces. So given let's say you have two maps to X. Here, for the sake of the definition, this doesn't have to be a covering map, but it might as well. Then a lift of F along P, if that's not obvious from the context, is a map F tilde from Y to X tilde such that P composed with F tilde is equal to F. So in pictures, this is, you start out with these maps, and a lift is an arrow there that makes this commute. So here's what we used for the case of the circle. Given a covering map, and a homotopy, right, there is you have to lift one endpoint first. A homotopy and a lift F0 tilde from Y to X tilde of F0. There is a unique lift of the entire homotopy that extends the lift of the endpoint, right? So if you prefer a diagram, that says that we have, to start with, a homotopy into X, a covering, and a lift of the endpoint map, and then there exists a lift of the entire homotopy, making this whole diagram commute. Okay, so if you look back to the case of the circle, we were careful when we proved it to give a proof that only assumed the properties that a general covering map has. So we've already proven this. So the proof we gave for the covering of the circle works in general. Okay, so we already have this. This is called the homotopy lifting property. Or if y is a point, then it's called the path lifting property. Okay, so that works for an arbitrary cover. Another fact that worked for us in the case of the circle, and that works in general, is that this uniqueness tells you that the the lift of a constant map is a constant map. So the lift of a path homotopy is a path homotopy, right? Because when you have a path homotopy, this is a homotopy that's fixing the beginning point and the end point of your path. So when you lift that homotopy, then in particular, you're lifting the constant map at the left endpoint and the constant map at the right endpoint. And so your homotopy upstairs also is the constant map at the left endpoint and right endpoint. This allows us to define what's called the lifting correspondence. Right? So just like the case of the circle, what we're really interested in is you lift the loop, and then you see what happened to the endpoints. Right? So you pick an initial endpoint upstairs that gives you a unique lift of the path, and the other endpoint has to be also in the preimage of your base point downstairs, but it might be a different element of the preimage upstairs. So it's the lifting correspondence. So given a covering map, and let's say with a choice of base points, then let phi, capital Phi, be the map that takes homotopy classes of loops based at x naught, lifts them up to a path starting at x naught tilde, and then picks the right endpoint. So you have a homotopy class here. You pick a representative, lift it up, and look at the right endpoint. Right? This is well defined because this is a path homotopy. Any two representatives are related by a path homotopy here. That homotopy lifts to x tilde to a path homotopy. So the right endpoint is going to be fixed no matter what representative we chose. Okay, so let's start looking at what happens to the fundamental group when you have a covering map. So if this is a covering space, then the induced map is injective. Okay. So there's no null space. And let's describe the image so the image consists of the homotopy classes of loops based at x0 that lift to x tilde two loops based at x0 tilde. So what you should think of is if I take a loop downstairs, then I can lift it uniquely as a path upstairs. But this path need not be a loop. What happens is that it starts at our base point, and it ends somewhere above the base point downstairs. But it doesn't have to end at the same part of the preimage upstairs where it started. So what we're saying here is that the image consists of those loops downstairs that just happen to have the property that when you lift them upstairs, they're not just paths, they are actually loops, right? So they do end back where they started. Okay. So another way of saying that is that the image is precisely, in terms of the lifting correspondence, it's precisely the ones whose right endpoint is the base point. Okay. Okay, so let's prove this. So the proof that it's injective is pretty easy. So if you have a loop upstairs, and when you project it down, you get 0 in the fundamental group, well, of course, that's the same as saying that if you pick any representative of this class downstairs, then that's path homotopic to the constant loop at x0, right? But now if I lift both of these paths, then, well, here I'll just get g. And here, the lift of the constant loop is the constant loop by uniqueness. And if I lift this path homotopy, I get a path homotopy between the two lifts. So this says that the loop you had upstairs is path homotopic upstairs to a constant loop. And that's the same as saying that you started out with the trivial homotopy class upstairs. Right? So there's nobody in the null space. On the other hand, let's say that you have a loop downstairs in the image of P star. Well, of course, that's the same as saying that if I take a representative, I can homotope it to somebody in the image right, in the image of the fundamental group. So it's the projection down of a loop based at x naught. But now I just lift both sides. And it's the same as saying that the lift is path homotopic to G, where G is some loop based at x naught. Right? So being in the image is the same as saying that when you lift, you get a loop. But this is a path homotopy. So far we've said that this is path homotopic to a loop upstairs. But it's a path homotopy. So if this is a loop, then this is also a loop. Okay. So just to see what this is saying, let's say you looked at S1 with base point 1, so we're thinking of it as being inside the complex numbers. And let's say that our map is C goes to C to the n. Okay, so this induces a map on the fundamental group. And a loop that goes around the circle once here, well, you're going to go around the circle n times here. So this map is Z goes to, an element goes to, an arbitrary element here goes to n times that element here. All right, so this is a map from the integers to the integers that just multiplies by n. Right? So the image, so we see that this is injective, and the image is precisely the loops that go around the circle n times, a multiple of n times. So of course, these are the ones that when you lift upstairs, since they went around a whole n times, then they closed up again upstairs. Right? So if we draw the case of 2, so let's say that you have these two loops over here, and so sorry, you have this covering space with 2 points sitting above each point downstairs. So if I have a loop that goes around here once, then when I lift it, starting at this base point, it's just going to go around until it gets to the other base point, and it'll stop there. But if I have a loop here that goes around twice, then up here it'll go from this base point first to this one, and then the other time around it goes from this base point down to this one, and so it ended up with a loop. So you can see that the loops down here that lift to be loops up here are precisely the ones that go an even number of times around, right, which is exactly this image. Okay. Okay, so here's the theorem involving this lifting correspondence. So say you have a covering, and let's say that x and x tilde are both path connected. Then if I look at the image, this is a subgroup of the fundamental group of X. And so I can look at the cosets. Right? I don't have any guarantee, at least not so far, that this will be a normal subgroup. So there's no group structure on this necessarily. But I can look at the cosets, and it turns out that our lifting correspondence, right, which remember just takes a loop, lifts it up to a path with a fixed base point, and then notices what the endpoint of that path is. Right? So this is well defined on these cosets, and lands you here. And the claim is that this is a bijection. Okay, so notice again that even though there's a group over here and a space over here, we're not claiming anything about continuity or homomorphisms or anything like that. We just have a map of sets, and the claim is that it's a bijection. So, for example, if you're looking at the real line mapping down to the circle, then the fundamental group upstairs is trivial because it's simply connected, because it's contractible. So this is just the identity. The cosets are just the fundamental group of S1. The inverse image of a point, right, was the integers. So we proved before that actually in this case, this is not only a bijection, it's actually a group homomorphism, isomorphism. Right? That was the proof, the computation of the fundamental group then. If you look instead at the map that we were just looking at, where you go around the circle n times, then what this says is that C mod NC, which in this case, this is a normal subgroup, but that doesn't matter. This set of cosets is in bijection with the inverse images of a point, right? So over here, right, where we had the case n equals 2, right, the image we saw was 2z, and so C mod 2c would give us a group with 2 elements, and of course the inverse image of this point has 2 elements. Right? So this is saying that that's no coincidence. The cardinality of either side is the number of sheets of the cover. Okay, so let's check that this is indeed a bijection. So let's give the subgroup a name. Let H be the image. Okay, so I want first to check that phi is well defined on the cosets, right? So the cosets look like something in this group multiplied by something in H. So let's say I have H times G with H and H. And G, the homotopy class of G, an element of the fundamental group. Okay, so phi of H times G is by definition, take this loop, view it as a path, lift that path, and then look at the right endpoint. So by uniqueness, the lift of this concatenation is going to be the concatenation of the lifts. Notice that this makes sense precisely because H lifts to be a loop at x naught tilde. And so, so this does end where this one starts. So it's just this path evaluated at the right endpoint. But because, so it's a concatenation, so it goes from the left endpoint of this one to the right endpoint of this one, which is the left endpoint of this one, and then to the right endpoint of this one. So this one doesn't affect where we end up. We end up with g tilde of 1, and that is phi of g. Right? So if you put concatenate on the left with an element in H, then because we saw that the lift of elements of H are loops at x naught tilde, this doesn't affect the right endpoint where you end up at all. So phi is well defined on the cosets. Okay, now phi is surjective because we've assumed that x tilde is path connected. So if you pick any point in here, there is some path in x tilde that joins this base point to the point you picked. And if you project that path down, you get a loop because the endpoints will both project down to x naught. Right? So you'll get a loop downstairs, and so it'll define an element of the fundamental group. And when you lift it up, since the lift is unique, you have to get that path we started with from x naught tilde to whatever point we picked. So surjectivity is immediate from path connectedness. To see that it's injective, well, assume that you have two cosets. So let's just don't worry about the cosets. You have two loops, and when you lift them, you get the same endpoint upstairs, right? So you have the same image under phi. Since they have the same image upstairs, so this is the same as saying phi, the lift phi1 at 1 is the lift of phi2 at 1. Then if you can do phi1 tilde and then do phi2 tilde in the opposite direction, and this will go from x naught tilde to this point, and this will go from this point to x naught tilde. So this is a loop in x tilde based at x naught tilde, which is equivalent to saying that this loop downstairs based at x naught, this is a concatenation of two loops, that this, the homotopy class, is in the image of P star, right? Because we've shown that the image of P star consists exactly of those loops downstairs that when you lift them up become loops based at x naught tilde. And of course, the lift of this concatenation is the concatenation of the lifts by uniqueness. And that is a loop. So this is in the image of P star, which is H. But then that tells you that the left coset, the right coset of F1 and the right coset of F2 are the same, which is what we wanted to show. Right? So if the right endpoints of the lifts are the same, then they come from the same coset. So that shows that this is a bijection. Okay, so this suggests that something special happens when this group is trivial, right? Because then these cosets are the same as the group itself, and so the group is in bijection with the inverse image of the base point. Right? So we give those covering spaces a name. A covering space is called A or D universal cover if x tilde is simply connected. Right, remember that means that x tilde is path connected. And that the fundamental group of x tilde is trivial. Okay? So that's called the universal cover. And so later we will justify the name universal cover and talk about in what sense is it unique when it exists. It's a quick application. Let's say you look at RPN. Right? So as you know, RPN is the projective plane, real projective plane of dimension n. So this is the set of all lines through the origin in Rn plus 1. So you can identify lines with just a couple of 2 points on the sphere, and so you're just taking the sphere and identifying antipodal points. So this has a natural map from Sn down, where you're just taking any point here and sending it to its equivalence class of it and its antipodal image. It's easy to see that this is a covering map, because just take any neighborhood of a point over here that does not intersect its just take a neighborhood here, and its lift will consist of 2 neighborhoods, 2 copies of that neighborhood, one around one point and the other around the antipodal point. So it's easy to see that this is a covering map, and the inverse image of a point, so this is a covering map, and the inverse image of a point has cardinality 2, and Sn is simply connected. So this is a universal cover. So it follows from what we just saw that the fundamental group of RPN mod out by the trivial subgroup, so not doing anything, has lifting correspondence to this set, and this is a bijection. So what that shows is that the fundamental group of RPN has cardinality 2, but there's only one group that has cardinality 2. So this is actually C mod 2C. Right? Of course, it's also easy to show this with Van Kampen's theorem using a cell complex description of the projective plane. And one of the problems on the homework is to do exactly that. Okay, you could use the same trick. Of course, all that mattered was that that we were looking at a universal cover and that the cardinality, that the number of sheets is a prime number, because then just knowing the cardinality of the group gives us the group. And so, for example, if you want to look at lens spaces, those are also quotients of the sphere. So that the sphere is the universal covering space, and in that case, you can, for any prime p, you have an instance where this cover has p sheets, and so the fundamental group has to be C mod pz. Okay. Okay, so here's another case where we're interested in a local property. We're going to say that y is locally path connected. So as I mentioned earlier, this is the same as saying that, well, anytime you use locally, it's the same as saying that this is true for arbitrarily small neighborhoods of a point. So in this case, that means given any point y in y and a neighborhood, then there exists a neighborhood V of y in y, V inside U, such that V is path connected. Right. So this requirement that given a U, there is a V inside it so that it's path connected, this is how we make sense of arbitrarily small neighborhoods. So that's what we mean by locally path connected. And for locally path-connected spaces, we have a general lifting criterion. Okay, so remember we given a covering space, we know how to lift paths, and we know how to lift homotopies. It turns out that the fundamental group will tell us when you can lift arbitrary maps. So the setup is that we have a covering map and a map and to xx naught. And we want to know when is there a lift. So there is a lift of f, i.e. a map from y naught to x tilde that lifts f if and only if the induced map of f sends the fundamental group of y into the image of the fundamental group of x tilde with respect to p, right? So, right, remember in terms of the diagram, what we have here is y tilde, and we're mapping this into xx tilde. We have xx naught. We have x tilde x naught tilde sitting above, and we want to know when can you construct the lift. Right, so this is like one of those classical applications of algebraic topology, because this question doesn't involve any invariance from algebraic topology. You have this cover, and you want to know if you can construct the lift, and it turns out that the answer is entirely in terms of invariance of algebraic topology. Right, so what you need is that when you take the fundamental map of this space and you map it over here, it lands inside the image of the fundamental group of this guy mapped along this map. Okay. So the fact that that's a necessary condition is very easy to see. So if there is a lift, then f is equal to p composed with f tilde. So the image of the fundamental group of y along f is equal to the image of the image of the fundamental group of y along f tilde followed by p. So, but of course this is a subset of the fundamental group of x tilde. So this sits inside p tilde of the fundamental group. Of x tilde. Oh, sorry, of course, I introduced this because we need this hypothesis. So this is here with y path connected and locally path connected. Sorry, so of course that's why I introduced the definition. So for this direction, of course, you don't need anything on y. If you have a lift, then the image of the fundamental group with respect to f tilde is inside the image of this fundamental group along p tilde, right? But to actually construct the lift, we want y to be path connected and locally path connected. Okay. Okay, so now assume that y is path connected, locally path connected, and the image sits inside the image. Okay. So now for each point, choose a path g sub y from y naught to y. Okay, so for bookkeeping purposes, let's say, we're just going to go ahead and fix for every point in y some path that goes from the base point to y. So we're using the fact that y is path connected. Okay, so the reason we do this, we have this map, and we have a covering map, and we want to figure out what f tilde of a point y should be up here, right? So given that we have a covering map, we know how to lift paths, right? So the idea is look at paths in y, because those will give you paths in x, and you can lift a path in x to a path in x tilde, right? So for each point, choose a path. Then f composed with gy is a path in x starting at x naught. Since P is a covering map, we can lift to a path in x tilde starting at x naught tilde. So let's define f tilde of y to be f composed with gy lifted, look at the right endpoint. Okay? So if we had f tilde, then by uniqueness of lifts, this would be its value at y, right? So this is a consistent definition if you actually do have a lift. And what we're going to show is that this does give you a lift. Okay, so the first thing we want to point out is that this definition is independent of the choice of the paths gy. Okay, so let g prime y be any other path in y from y naught to y. Okay. So consider H naught. It's what you get by taking the concatenation. Okay, so we know that G prime and G have the same endpoints. So if you send them over to X using F, then you still have the same endpoints, but now you're in X. So this is a path in X, and this is a path in X. They have the same endpoint, so if I take the reverse path, then I end up with a loop. In X, based at X naught. But of course, H naught is equal to F composed with G prime dot G. So the homotopy class of H naught is inside the image of pi 1 of y along pi 1, no, sorry, along F star, and that sits inside the image of the fundamental group of X tilde along P star. Right? So that says that H naught is path homotopic to some image of, G is not a good choice, to the image of a loop upstairs along P. Right? So, okay, a loop at X naught tilde. Okay, so we can lift this path homotopy. So by uniqueness of lift, it's the same as saying that H naught tilde is path homotopic to K. This is in X tilde. Now, by uniqueness of lifts of paths, the lift is the same as lifting this and then lifting this. Right? So as paths, there's only one way of lifting it, and so you get this. But in particular, this means that so if you like, think of taking the first half of H naught, right, and then lifting that, and then similarly with lifting the second half of H naught and lifting that. So uniqueness of lifts tells you that those two lift to be the corresponding halves of K. So the first half of K and the second half of K. But the fact that they lift to give you a loop upstairs means that these are compatible. So when you lift this one to start at X naught tilde and you lift this one to end at X naught tilde, so that you're lifting to the two halves of K, what you get is that they have to have the same endpoint in the middle here. So we conclude that the lift of this at 1 is equal to the lift of this at 0, which is the lift of this at 1. Right? So, and of course, this is how we decided to define F tilde of, please have Y's, F tilde of Y if we had used gy prime, and this is how we would have defined f tilde of y if we were using gy. And so this shows that it doesn't matter which one we use, we get the same definition of f tilde of y. So we have a well-defined map, and it's clear from the definition that it is a lift of f, right? And so you can see that, of course, because you're just lifting this path to a path in x tilde. So the right endpoint here lies above the right endpoint here, but that right endpoint is just f of y. Right? So it's clear that this is a lift of f. So all that's left to check is that this map we've defined is continuous, right? So after all, we defined it by taking an arbitrary path in y and then lifting. So there's no relation implicit between the g sub y's for nearby y's. Right? Do just whatever path you want. Okay, so pick a neighborhood of a point f of y that is evenly covered by P, and let V be the slice above it containing f tilde of y. Right? So we've defined f tilde of y. It's some point lying above f of y. So it's contained in one of these slices, which we denote v. Okay, so pick any other point. So we can define f tilde of y prime using a path gy prime that let's say it like this. This is equal to gy dot ky prime. So, all right. So let's say that this gy is the original path that we chose that gets you to y. Right. So fix that path. To define f tilde of y primed, you only need some path that gets you to y primed. So let's say that you take the path that gets you to y, and then you just continue with some path that goes from y to y primed. And now we're going to use that y is locally path connected to say that, that we can choose this path from y to y prime that stays in v. Right? So we can choose this final part of the path staying entirely inside v. Excellent. But the lift in V is really easy because the restriction of P to V, this is a homeomorphism. So we have an inverse map which is continuous. So if you want to lift a path from U to V, you just compose it with this inverse map. So in fact, you can see that F tilde restricted to V is just P restricted to V inverse composed with F. So F tilde is continuous at Y. And since Y was arbitrary, F tilde is a continuous map. Okay, excellent. So that's the lifting criterion. It tells us when you can lift. An easy fact is that if lifts exist, they are unique. So specifically, let's say you have a cover and you have a map with two lifts. So if Y is connected, and these two lifts agree at a point, then they agree everywhere. Okay. So this, of course, is easy. So let's say you look at a point in Y, and let U in X be a neighborhood of f of Y that is evenly covered by P. So let V1, V2 be the slices containing F1 tilde of Y, F2 tilde of Y, respectively. Right? By continuity, if F tilde is mapping Y into V1, then there is some open neighborhood of Y that gets mapped to V1 by F tilde 1. And similarly for F tilde 2. And taking the intersection of those neighborhoods, we can find a neighborhood of Y such that Fi tilde of n sits inside Vi. Okay, so if F1 tilde of Y is not equal to F2 tilde of Y, then V1 is not equal to V2. So F1 tilde is F1 tilde of Y primed is not equal to F2 tilde of Y primed for all Y primed in N. On the other hand, if f1 tilde of y is equal to f2 tilde of y, then since p composed with, let's say then v1 is equal to v2, and p composed with f1 tilde y prime equal to p composed with f2 tilde y primed implies f1 tilde of y prime equals f2 tilde of y prime for all y primed in N, because P is a homeomorphism from V1 to U. Right? In particular, it's injective. And so these are equal. So this shows that the set where f1 tilde is equal to f2 tilde is open and closed. And so is equal to all of y. Okay. Great. So let me just finish with relating this to our homotopy lifting property, because we've seen that you have an arbitrary lifting criterion with a condition on the fundamental groups, and we've seen that you have a homotopy lifting property, and there was no discussion of the fundamental groups. So of course the point is that we did have a hypothesis. Our hypothesis was that you had a lift of the left endpoint. Right? So remark for homotopy lifting. Remember, our initial data is this, right? And so to have a lift of this map, what we need is, by our general criterion, we need that the image of the fundamental group of this in here is in the image of the fundamental group from here, right? But of course, y times the interval, it has the left endpoint as a deformation retract. So the fundamental group of this is going to be the same as the fundamental group of this, and the image over here is going to lie inside the image like this, and so in particular the image of P star. So for homotopy lifting, the initial data, or let's say the initial setup, implies the general lifting criterion. Okay, so we'll pick it up from there on Thursday.